Hi, I'm Calvis Rice, and I'm the Director of Business Development at IPS. This is part two of our Can School educational series of how to make more quality cans. In part one, we presented the idea that making more quality cans is a two-step process. First, we have to focus on making more cans, which means decreasing downtime and spoilage. Our focus is going to be specifically on the Bodymaker. In part one, we talked about alignment, and now we'll be discussing tooling. Tooling caused spoilage and downtime comes primarily from surface finish related issues as well as geometry related issues. And poor tooling surface finish causes issues such as tear-offs or short cans, which is the main issue of poor tooling surface finish. Now, most tear-offs or short cans come from an incorrect surface finish on the punch. And before I dig any deeper into eliminating tear-offs, I want to point out that we have done an in-depth Can School lecture on the science of tear-off reduction. I encourage you to visit our website or our YouTube page to watch the entire lecture. A few things I do want to point out are that tear-offs occur when metal slips on the punch during the ironing process. So the punch must have a surface finish applied, and the crosshatch is an ideal surface finish to eliminate tear-offs. Moving on, poor tooling geometry control causes issues when changing tooling. So we've seen many plants with this situation where a Bodymaker operator selects a tool based on a progression chart, inserts it into the Bodymaker, yet the can that results is out of spec. And what ends up happening is that doubt is placed in the mind of the Bodymaker operator as well as toolroom personnel, and we no longer trust the diameters or sizes that are written on the tooling, and we have unreliable inventory. To dig into why this happens, we're going to dig a bit deeper into what a Bodymaker progression is and specifically how tooling sizes are selected for a tool pack. In this animation, we're going to see how the cup drops into the Bodymaker, and the first step is it will go through the redraw die, which changes its diameter into the ultimate diameter of the can. After this, which will be our focus, is the ironing dies, which will thin the metal, grow the can, and in this detail, we will see this specifically happening. Now, the key word here that we want to focus on is a reduction. And so going into the ironing die, we have a pre-iron thickness of metal. And here we have a thinner post-iron thickness. So the reduction refers specifically to how much the metal is thinned in the ironing die, expressed as a percent. And so typical rules for the can making industry are that the first ironing die does a reduction in the mid-20s. The second ironing die also, the reduction is in the mid-20%. And the third ironing die does the most work, and its reduction is in the low 40s. Rules are meant to be followed, and the rules of reduction, when they are not followed, specifically in the third ironing die, where if reductions much exceed the low 40%, processes become less stable and issues start to pop up. Tensile tear-offs or short cans are one of these issues that can happen, so it's important to follow the rules of reduction. Now we're going to take a look at a sample progression chart. And so every tool room has one, but I'll walk you through the basics of it. We have here the punch, the redraw die, the first, the second, and third ironing dies. This shows the reduction of the third dies, the second dies, and the first dies. And so this is obviously a small sample of the numerous lines that a progression chart would have, but it's important to point out that each line of the progression chart is separated by a 10,000th of an inch. So when looking to build a tool pack, it's important to be able to go on a complete line of the progression chart. So the ability to repeatably measure tooling to the fourth decimal place is essential. So when tool changes occur and they don't produce predictable results, oftentimes it's the tool measurement gauge that is at fault. There's two types of tool measurement gauges in our industry. The first is contact gauges. The second are non-contact gauges. And we're going to look at the differences between these two classes of gauges by looking at three factors. First, contact gauges use measurement probes. And these here are seen, for example, on this tri-mic, that these probes come directly in contact with the tool. This probe here can be configured in various ways to measure diameter of punches. And with this type of a probe, again, the probe comes in contact with the tool. Non-contact gauges use non-contact technology. So here, the ToolScan 2.0 uses green LED micrometers to measure the tooling. Contact gauges typically measure single tool geometry and type, meaning that this tri-mic will measure dies and only the inner diameter of those dies, where non-contact gauges are more versatile. They measure various tool geometries and tool types. The ToolScan 2.0, for example, measures Bodymaker punches, dies, and more. Contact gauges have fair accuracy and repeatability, where non-contact gauges have excellent accuracy and repeatability. And the best way to show how non-contact gauges look is by showing you a couple of videos. On the top, we show the ToolScan 2.0 measuring a punch, and on the bottom, an ironing die. It's important to show that it being a non-contact gauge, the green LED micrometers, of course, never contact the tool itself. Another thing I want to point out is at the bottom, we're showing the ToolScan 2.0 being used with the tool control system. So right there, the barcode scan that is happening will connect with the tool control system, which is our tooling inventory and tooling tracking software that we'll be releasing in 2020. We'll have more on tool control a bit later. It's important to say that unreliable inventory is corrected simply by gauge accuracy and repeatability. So to see if your toolroom gauge is performing as it should be, we've given you a quick test. So go to your inventory and randomly select 10 tools. Then record the marked diameters on the tools on a sheet of paper, after which I want you to erase those markings from the tools. Then go ahead and remeasure all 10 of those tools and compare the original value with the new value. If there are any discrepancies between old and new, you likely have a gauge performance issue. And these discrepancies in measurements would likely cause performance issues when inserted into the Bodymaker. So remember that the lack of repeatability is often the fault of the gauge and not the operator. A toolroom operator can only do as good as the gauge they are provided with. So now that we've talked about the first step of making more quality cans, which is reducing downtime and spoilage by Bodymaker alignment, talking about tooling surface finish, and now understanding the importance of a repeatable tooling measurement system, we can move on to the second step, which is improving can quality. We've broken up can quality into three main categories. The first one is can performance, the ability for a can to withstand axial load, to withstand internal pressure requirements, as well as the ability to withstand the corrosive nature of the product that the can will ultimately be filled with. And all three of these gauges shown here, as well as many other, are provided by Sencon. We recommend that you visit Sencon's website or you contact a local sales representative and let them tell you more about the comprehensive solutions that they have for the two-piece can industry. The second category of can quality is aesthetic quality, which in essence mean how does the can look, how does the finished can look in your hand. And the third category of can quality is optimized can weight, and this will be our focus. So let's bring it back to big picture and say that can plants make two products. The first one is obvious, it's cans. The second one, which is going to be the focus that we'll take, is the scrap from both cupper and the trimmer. And so cans are sold to the customers based on a price per can, which means that the can value is based on quantity. The more cans you make, the more money you make. Where trim scrap is sold back to the aluminum mill based on a price per metric ton, which means that trim scrap value is based on weight. Copper scrap is very predictable and it does not have much variation. Once the die set is installed and things are running, there is not much variation in the scrap. Trimmer scrap, on the other hand, is much less predictable and it can have significant variation. And this variation is based largely on tooling geometry. So when we say we want to optimize can weight, we mean that we want to minimize the aluminum in the can and move it to the trim scrap. So by optimizing can weight, we also optimize trim scrap weight. And something worth pointing out that this little ring of trim scrap right here may not seem like a lot, but for a can line that is making 1 billion cans a year, that trim scrap can be worth up to $500,000 a year. So optimizing trim scrap, we have to look at the can profile and the tooling geometry. So looking at the can profile, we're going to look at this section right here first. And this is the mid-wall to dome transition. And two things that I want to point out here is that first, we have thin metal up top, and second, that thin metal transitions to thicker metal at the bottom. Now that transition is important for two reasons. First, it allows the can to withstand an axial load. But secondly, it gives a nice smooth transition between the thin and the thick metal found at the dome. Now the mid-wall to dome transition is a direct reflection of a feature on the punch called the rework taper. The second area of the can that we want to look at is at the top right here. And this is the mid-wall to top wall transition. Again, we have thick metal up top and a transition to thin metal. Now, the thicker metal up top is required for the necking process. And the mid-wall to top wall transition is again a direct reflection of a feature on the punch called the transition or the step. So now that we understand that the rework taper and the punch step are important features, we want to show you that it's important to control both of these profiles because if they are not, 25% or more of the trim scrap can easily be left in the can. So it's important to control your tooling geometry. So how do we control it? First, we want to talk about tooling inspection. It's important to measure your major diameter. It's important to inspect your step, to inspect your body taper if your punch calls out for one, and also your rework taper. And the key is to start with a good punch. How can we expect a good can if we don't know that the punch producing that can is to spec? So it's important to inspect all critical geometries before inserting a tool into a Bodymaker. The ToolScan 2.0 has a great feature called the punch scan, and the punch scan allows the user to see in detail the exact profile of the step and compare it to that called out on the print for that punch. The second way we control tooling geometry is by using high quality tooling. This all starts with your supplier. So we want to have inspect tooling delivered from the factory. We also want to make sure our tooling is of quality materials. And one of the characteristics of a quality material is its resistance to abrasion. And so the key here is to select a quality supplier. And we must be able to rely on our suppliers to provide consistent, timely delivery of quality tooling. Hyperion is one such quality supplier, and they have become one of the best suppliers in our industry. Hyperion has a premium grade carbide I want to talk a bit about, which is DZ18, and it has a number of characteristics which are worth pointing out. First off, it has a resistance to abrasion that is much better on the premium grade than on the standard grade. The density of the premium grade accounts for a 15% lighter punch when compared to a standard grade carbide. And all of this also gives 2 to 4 times more tooling life when compared to standard grade carbide. So when we talk about the DZ18, the higher wear resistance, that's important in making more quality cans, because if we know that the punch has certain geometries that are important to keep as they are, higher wear resistance allows us to keep the size, the profile, and the surface finish on the punch for a longer period of time. The lighter weight punch gives us a couple of benefits. It reduces ring consumption, improves top wall concentricity, and allows higher Bodymaker speeds. I recommend you contact Hyperion, talk to your local sales rep, and see if DZ18, the premium grade carbide, is a good fit for your plant. The third thing I want to talk about in controlling tooling geometry is process. So tooling inspection is important, but the process behind it is also. So it's important to inspect all tools before they end up on your inventory shelf and of course into your Bodymaker. It's important also to make sure that your tooling temperature has stabilized before measuring them. Tooling surface finish is of course important. To reduce tensile tear-offs, we need to apply a crosshatch surface finish. And now that we understand the critical geometry and profiles on the punch, it's important to eliminate manual hand crosshatching of punches. A controlled process like the X2 crosshatch machine is far superior than hand pressure. Imagine hand pressure crosshatching destroying your step or rework taper. So important tooling surface finish process means a machine that can repeatably apply this surface finish. Another thing I want to point out is respecting the rework taper. So never polish the rework taper. Polishing a rework taper can have two potential issues. First, we are changing the profile of the rework taper, which means that more metal can potentially be added to the can, and that metal is robbed from the trim scrap. Secondly, a non-surface finish or the wrong surface finish on the rework taper can actually increase in hubcap style tear-offs. Finally, Bodymaker basics. So making sure your Bodymaker is aligned properly and it is maintained as it should be, making sure that the Bodymaker performs as it should. Finally, I want to talk a bit about the ToolScan 2.0, give you a bit more information about this gauge. It measures Bodymaker punches and dies, specifically IDs of ironing dies and redraw dies. On Bodymaker punches, it measures the OD, the rework taper, the step. It has a nice scan feature that allows you to inspect it, which we showed you previously. And very exciting for IPS is that at the beginning of 2020, we will be releasing new capabilities of this gauge. And the ToolScan 2.0 will be able to inspect necker tooling, and it will also have roundness capabilities. The ToolScan 2.0 is the most repeatable gauge in our industry at 15 millionths of an inch or 0.38 microns repeatability. And it does all of this very quickly, so no size measurement will ever take longer than 15 seconds. It's also worth pointing out that the fixtures for Bodymaker punches and dies never have to be removed to switch between a punch and a die. So it's very easy to use, very quick to use. There's a remote support module in the ToolScan 2.0, which allows us to regularly communicate with customers around the globe. We help with training new staff. We help with inserting new profiles of tooling into the system. And in the worst case, if anything were to go wrong, it allows us to remotely troubleshoot a system. And the ToolScan 2.0 is designed to be integrated with Tool Control, which of course is our tool tracking and inventory control software that will be released in 2020. This concludes this CAN School educational series. If you learned anything from this video or you liked it, please share it with a colleague or like us on YouTube. If you have any questions, please give us a call, send us an email, or visit our website. Thanks for watching.